Okay, welcome to our first video lesson for Year 11 Physics. Hopefully you're all holding up okay. Today, what we're going to look at is sea breezes and the location of the world's deserts, which is two things that seem like they have nothing to do with each other at all. But actually, they're both related to this thing called a convection current. So the physics that we're learning today is convection currents, and the two applications we're going to look at are sea breezes and the location of the world's deserts, which might seem very strange, but that's what we're doing. So by the end of the day, we're going to be able to predict where sea breezes are going to form and say whether they're going to be coming onshore or offshore, depending, it turns out, on the time of day. And we're also going to be able to explain the position of the world's deserts somehow. Okay, so let's start with just what convection is. So what I've got here is just a beaker. And what I'm going to do is I'm somehow going to heat up one little spot of the water. It doesn't really matter where, but let's say we have a little flame here. Right. So now the area underneath, the area at the bottom here, this water here, is going to be hotter than the rest of the water. So I'm just going to represent that with a little red patch. Here we go. We got a little patch of water here that's hotter than the rest of the water. And what fluids do, so by fluid I mean either a liquid or a gas, what fluids do is that when they get hot, they actually expand. So instead of being, once it gets hot, instead of the patch being that size, it sort of expands out to that size. So we got the same amount of water, but it's taking up more room. The other thing that's true of fluids is that if you have less density, that is less mass per volume, so let me put that on the side there, density equals your mass divided by your volume, objects with the lowest density rise upwards and objects with the higher density drop downwards. So what's going to happen to this little patch here is it's actually going to start rising upwards because it's of lower density than the water around it. That's called buoyancy. This, by the way, is why humans float on water, is because we're actually slightly less dense than water. We're almost 75% water, but the things that we have that aren't water are actually less dense than water. So if you just stand still in water or stay perfectly still, you'll actually bob along the top of the water rather than sinking downwards. So what happens is that little patch of water heats up, it moves upwards, and of course that leaves behind a little hole in the water that some of that cold water at the bottom here is now going to rush into. But then what's going to happen to that cold water? It's going to get heated by the flame again, so it's going to start rising. So we're starting to get a sort of a process where the water rushes in from the sides and then goes up. Once it gets to the top there, it's kind of got nowhere to go. So it separates out. And of course, this cold water here rushing in from the sides, in like this, it also leaves a gap behind here and here, which means the water from above has to rush in to fill it. And we end up with these sort of circulating currents driven by the heat flow. So these things here are called convection currents. I'll link a couple of videos below that show you just what it looks like with a bit of ink or whatever. I tried to do it with myself, but I didn't have any food dye, so I tried to use tea. It didn't work out too well, so I'll just link to some videos. Okay, so that's the basic of a convection current. That's one of the three different ways that temperature can be dispersed. So temperature can flow between materials. The two that we've sort of thought about so far are conduction. That's where two things are just physically in contact and the atoms are bumping into one another. We've talked a little bit about radiation. That's where the objects are emitting light, We often think of that as infrared light, but it doesn't need to be just any light because it's hot, basically all that black body stuff. Um, and of course, that's going to be moving heat from one object to another, because if I'm emitting it and it's hitting you, then I'm giving you heat. So radiation is... And then convection currents are sort of the third and final way that you can move heat around a system. It only happens with fluids, which are gases and liquids, because obviously solids can't do this whole flowing situation like this. Just another reason why liquids and gases are different from solids. All right, so let's look at our two case studies. Our two case studies are onshore breezes and offshore breezes, and the location of the world's deserts. So what I've got here is a little picture of a coastline, and we've got some people playing cricket there. That's in honour of the Fremantle Doctor, which, if there's any cricket fans, you know, famously at the Wacker, yeah, used to play in the middle of summer in Perth. It'd be like 35, 40 degrees all day, and the cricketers would be run down, the bowlers would be stuffed after a day in the field. But at 4 o'clock, reliably, every single day, you would have this lovely breeze running in off the coast of Fremantle onto the cricketers, cooling things down. And that was it was always in the last session of the day. You'd always have this nice breeze coming on. So how is it that we can predict that there'll always be a nice cold breeze coming in at a certain time of day? And it has to do with these convection currents. So let's walk through the argument. Okay, so it starts with the observation that water has a much higher specific heat capacity than pretty much anything else, but certainly than rock and grass and concrete and land, right? So rock and grass and concrete and land typically have specific heat capacities like 2000. The other thing that's true of water is if you heat the top little surface of water, that water will quickly dissipate into the rest of the water using those convection currents and stuff that we've been talking about. So that's a different application of convection currents. We won't talk about too much, but that heat's going to sort of get dissipated through the whole surface. On the other hand, a rocky surface or a grassy surface, or land basically, only the sort of the top layer of the surface is going to hold all of that heat. So what you end up with is that the heat is only very slowly dissipating down into the ground. So you end up with a very hot surface of land, but if you go down 10 meters below the surface, it's going to be cold again. So what that does is that creates a temperature difference between the sea and the land as the sun beats down during the day. So as the same amount of heat energy from the sun lands on both the water and the ground, but the ground's temperature shoots up significantly, whereas the water's pretty much stays at the same temperature. Right. So what that's going to do is that means the air that's closest to the land is going to start getting hot. So by the end of the day, by 4 o'clock in Fremantle, you've got a land that's really hot, and you've got a thin layer of air above that land that's also really hot. And so what happens is, well, that hot air is less dense than the air either side of it, and certainly above it. So that air starts rising upwards. Okay, then what happens? Well, you've got a little gap here where that air's just disappeared from. Let me sort of make it clear that that's happening all across the land. You've got a gap, little pocket where that air is now missing. So what happens is the air that was above the ocean comes rushing inwards to fill that gap. So this is what we call an onshore breeze. Onshore breeze. And now, of course, that air has to go somewhere. It can't just disappear. So this air up here then circulates out this way and drops downwards. Oh, let me get blue. Drops downwards, completing the cycle. And once again, we have one of these convection currents. moving in this direction, but in particular coming onto the ocean by the end of the day. Now, the hotter the day, the earlier this will happen, because that ground will heat up quicker. And if it's a cold day, you might not get much of one. But pretty predictably, if you live in a coastal area, if you've got a hot, dry day and it's baking the ground all day, then by the end of the day, you're going to have a nice breeze coming in off the ocean, which is one of the reasons it's nice to live by the sea. Now at night, this whole process reverses, and oh god, I haven't drawn a picture already, so I'm going to have to very quickly knock one up. It's not going to have lovely cricketers and stuff on it, this one. This one's just going to be land, water. Okay, so then let's reverse things. Let's say it's now nighttime. I don't know if that shows up. There's my crescent moon. Oh yeah, that shows up right. Now at nighttime, we said that during the day, all that heat goes into the water and it just gets stored below high heat capacity water. The temperature doesn't change much. On the other hand, the ground got hot. But during the night, because the ground hasn't actually absorbed very much heat energy, it's hot, but it has a low specific heat capacity, and only that thin layer has actually been heated, it actually gives up its heat really quickly. And so within a few hours of nighttime, we don't have really hot land. We actually have land which is much colder than the ocean, right? The ocean is actually now warmer than the land because the land gives up that heat really quickly. So what that means is now, relatively speaking, the ocean is the warm part and the ground is the cold part. And the breezes are running in reverse. So this is called an offshore wind. And that tends to happen overnight. Okay, so during the day, especially at the end of the day, once the ground's got nice and hot, you always get an onshore wind, and at the end of the night, you always get, in the middle of the night, you tend to get an offshore wind. So this is one of the big drivers of wind in seaside areas. Okay, cool. That's application one. Now for application two, and that is the location of the world's deserts, which I think is more mysterious. I think we can understand on one level why winds should be driven by convection currents. Why on earth would the world's deserts be driven by convection currents? So the first thing to note about the position about the world's deserts is that if you look at a map of the world, they're not just randomly scattered. It's not the case that the world's deserts are just any old place. They tend to be sort of in this band about 30 degrees above the equator. And so that's the world's really biggest deserts, like the Sahara, the Arabian Desert, the Gobi. And the only place where that's really broken up is where we have big mountains, like the Himalayas, which kind of break the cycle a bit. And then we have over in America, we got the Sierra, oh God, Atacama Desert. You got Death Valley. The Sierra Nevadas are in here. They create a bit of a rain shadow, but we got desert region here, desert region here, desert region here, desert region here. And then if we look below the equator, sort of about an equal distance, you've got the deserts of South Africa, you've got the deserts of Chile, and you've obviously got the desert continent of Australia, which we think of it as having nice farmland and stuff, but that's really only in these tiny little regions in the corners. Australia is basically a desert. And if you notice, they're sort of equidistant from the equator. So that suggests that there's some mechanism here. This isn't random. And it turns out that convection currents are the answer. So let me show you what that looks like. Okay, back to my little sketch pad. Oh, where did I do it? Oh, over here. Okay. All right. So Here is a little picture of the world. And where are the deserts? The deserts are kind of here-ish and here-ish and definitely here-ish, the Sahara, and definitely Arabia, and a fair bit of Mexico, and California's up here, and so forth. So we've got our deserts there. So what's going on here? Well, let's use a similar mechanism to what we were talking about. If we're going to get convection currents going, there always has to be a hot spot and a cold spot. And if you think about where is the hottest spot on Earth, it's around the equator. It's getting the most sunlight per day. So it's as if we've got the Bunsen burner right there on the equator. So what we get is around the equator, the air and the water and the land, and especially the land, gets really, really hot. Okay, what does that do? Well, I'm just going to draw this on the sides here. That air from the equator is going to rise upwards, right? And so it's going to be hot. It's going to have heaps of moisture in it, and it's going to rise upwards, and it's going to cause a lot of rainfall around the equator. So we get a lot of we get rainforests. We get really lush places directly around the equator. And then, of course, just as always, we have air's going to rush in to fill the gaps left behind by that. And then we're going to get those convection currents going again, the ones that we've seen a few times before now. And now we're going to have that cold air coming down the way. And it turns out that just because of the exact temperature gradients on Earth and because of the momentum that these things build up and da-da-da-da, it turns out that that whole convection current circle takes up about 30 degrees of the Earth's latitude. So at 30 degrees, that's where that cold air comes down. Now you might say, why would cold air cause a desert, which we associate with being really hot? Well, the thing about cold air is it doesn't hold very much water, and any water that it did have got picked up ages ago and has already been dropped. So all this air coming down, more important than the fact that it's cold, is the fact that it's dry. And so it's dry, it doesn't bring any water, there's no rainfall at these latitudes. So we end up with deserts. And then why do deserts feel hot? Well, back to that onshore breeze example, deserts feel hot because the ground heats up really quick because it's got no water in it. Water holds a lot of heat for a little bit of temperature change. Rock and sand does not. Rock and sand gets really hot with only a little bit of heat energy. Okay, so let's make sure we can go back to our learning intentions, make sure we understood it. So we understand how sea breezes form. The Earth gets hot during the day, air rises over the sea, then air rises over the land, and then wind rushes in from the sea to fill the gap. And then during the night, we get an offshore breeze because the opposite effect. The ground gets really cold because it doesn't have much heat capacity. The air drops there and then rushes out onto the sea, where the sea is relatively warmer and the air is rising. Why are the deserts where they are? Well, similar idea. The equator is hotter than everywhere else, so the air rises over the equator, goes through in these big convection cycles in the atmosphere, and then comes down at about 30 degrees latitude. And at 30 degrees latitude, that's where we find all of the world's deserts, because the air coming down is not just cold, it's also dry, because it hasn't seen the ocean in a long, long time by the time it gets there. Okay, that's lesson 1 over. Hope you learned something. Thanks. Bye.